Good morning and welcome to B-Sides Las Vegas, the ground 1234 track. We have a few announcements before we start. We have the SSO Wars, the Token Menace by Oleksandr and Alvaro. I was joking with him that I cannot roll my R's. My wife speaks Spanish and makes fun of me. Before we get started, though, we'd like to thank our sponsors, especially the Inner Circle sponsors, Critical Stack and Valimail, and our stellar sponsors, Amazon, BlackBerry, and the National Security Agency. It's their support, along with our other sponsors, which allows us to make this whole thing go on. Since these talks are being streamed to YouTube, we ask that you please silence your cell phones before we begin, and that you use a mic. If we have time for questions, we should at the end. Please raise your hand and I'll run the mic to you so that the people listening on YouTube will be able to hear it. If you have feedback about this talk or for the speaker, there's a link on the SCED entry for this talk. And with that, let's get started. Please welcome Oleksandr and Alvaro.
Okay, can you hear me? More or less? Okay. So thank you all for attending our talk. This is the Token Menace. My name is Alvaro Munoz. This is Oleksandr Mirosh. We are both security researchers with Micro Focus Fortify team. He specializes in dynamic and runtime. I specialize in static analysis, so a little bit different fields. So this is the agenda for today. We will start with a brief introduction to what authentication tokens are, especially in the context of delegated authentication. And then we will be presenting a couple of vulnerabilities that we found related with authentication tokens, both of them in .NET frameworks and .NET libraries. So the first one is an injection vulnerability that leads to arbitrary constructor invocation. This doesn't seem like very dangerous, but we will see what's the potential impact of this vulnerability. And then we will present an XML signature verification bypass that allow us to basically sign any SAML token and get the server to accept our SAML tokens as valid. So we will see how that affects several of the Microsoft frameworks, such as WCF and WIF, Windows Identity Foundation, and some major Microsoft flagship products, such as Exchange and SharePoint. So this brief introduction, this is a diagram representing delegated authentication. It's not supposed to represent anything specific like WS Federation or SAML protocol. It's just a very generic diagram, right? So basically, we have three different entities. The first one is the user that will try to access a protected resource that is served by the service provider. And the service provider is actually not handling authentication itself. It's actually delegating authentication to a third-party entity. Those the delegated authentication name. So it will redirect the user to this identity provider, and the user will basically present the credentials to the identity provider. It will verify the credentials, and if the credentials are valid, it will handle a token to the user that it needs to present at the service provider in order to access the resource. So this is basically a summary of delegated authentication. So these tokens that are returned by the identity provider can be in multiple formats, right? Like SAML or JWT, JSON Web Tokens, or simple web tokens, or any other, really any other format. Most of them have some similarities, and they have these major or important attributes, right? So these are the attributes that really are important to make a token functional. The first one is the issuer. So that's who issued the token. It's not the same if I give you a coin that I issued myself, that if a bank gives you a coin that they issued, right? So we also have the audience, that is who this token is for. So yeah, again, it's not the same if we create a token for service A, this token is not valid for service B. And if service B accepts a token for service A, then there is a vulnerability and something that we can exploit. We also have the expire date. Obviously, we can use a token after that date. And then we have a set of claims. The claims are basically a set of attributes that describe the user, right? So this will be used by the service provider for taking authentication and authorization decisions. But the most important attribute here is the signature, right? If we don't sign the token, anyone can change any of the claims, any of the issuer, the audience, anything in the token, and then get the service provider to accept that token as a valid token. And then the attacker will be able to basically become anyone who wants to be in the service provider. So there are multiple steps that an attacker can think about attacking. But the most important one is for us, or the one that we focused on, is step number 6, when the user presents the authentication token to the service provider. The user or the attacker, obviously. So the service provider needs to parse and process the token. And basically, it needs to verify all the attributes and also verify the signature. If the signature is not valid, then the authentication token should be discarded. So we will be focusing in this step because we found 2 different interesting attack vectors in this step. The first one is, what if we can inject any malicious string in any of these attributes that gets parsed before the signature verification? So maybe that can lead us to some kind of injection before the signature is verified itself. And the second vector is, well, maybe we can go one step further and actually bypass the whole signature verification process. So if we can do that, it's like the holy grail, because yeah, we can basically modify any claims in the token, modify the user ID, the user email address, and just authenticate as any arbitrary user. So now we will see these 2 vulnerabilities that we found in .NET Framework, and we will start with a token parsing vulnerability.
This case is a good illustration for token parsing vulnerabilities. JSON Web Token, or just GWT.
Louder. We can't hear you. Louder.
Or GWT is internet standard for creation JSON-based access tokens. We can see such token on the screen. It contains 3 main parts: header, payload, and signature. ILG field from the header defines what algorithm should be used for signature verification. So it will be used before we know it's valid signature or not valid signature. .NET has a couple libraries that can be used for GWT token parsing, and we found out that System Identity Model Token GWT library passes this ILG field to crypto-config create for name method. We noticed that this method doesn't restrict type names. So we are able to invoke arbitrary, no-argument public constructor. By the way, this method can breach not only just GWT tokens. The similar problem is in SAML token as well. For example, algorithm attribute in signature method element of SAML token will go to this method without any restriction as well. But you can ask what we can do with this, because we are not controlling any data. But actually we can control some data. First of all, it's type name itself. We will show a bit later how we can use it. Also, please pay attention on the gadget on the screen. It is from .NET Framework. And in .NET, current HTTP context is stored in static property. And access to request parameters is done through it. So if no argument constructor uses this approach, it can be very interesting for an attacker. But these ideas with abusing no argument methods may look not very realistic. So we decided to take 2 servers from Microsoft, this SharePoint server and Exchange server, and try to explore this problem there. And here is our result. SharePoint returned us different results if object was created or not. We can use it for getting information about installed product and even their versions. Also, we were able to raise unhandled exception that leads to denial of service. Exchange server gave us even more interesting results. As we already mentioned, we are controlling type name, and it may be not just simple type name, but assembly qualified name with assembly that we would like to load this type from this assembly. .NET allows to control developers assembly loading by implementing own custom assembly resolvers, and they may contain a lot of vulnerabilities. Also, often these custom assembly resolvers are installed by static constructor, and usually it is not a big problem to invoke them by instantiation specific type, and we actually can do this by this problem. But this attack is not simple, and sometimes even if we are able to add our assembly resolver and this assembly resolver has some vulnerability, we may still not be able to perform attack. For example, if a server has some assembly resolver before the attack, and this assembly resolver raises exception for our malicious assembly name, our new assembly resolver will not be called. Also, most of our gadget, what we found, allows us to load libraries from local disk. So attackers still need to find a way how to upload malicious file to the server. Here we can see examples of such assembly resolver gadget from an Exchange server. On the first snippet, it is installed by static constructor. On the second one, we can see assembly resolver itself. It uses assembly name for path for assembly loading, but no validation at all, so we can use .trick and change current folder to any desired what we want. Let's put all this together. As an authenticated user, we can invoke arbitrary public no argument constructor for any DLL file from any folder on the server. Of course, attackers still need to upload this file on the server. And for an authenticated user, it may be a very tough task, but it can be significantly easier if attacker has some account on the target Exchange server. So for our demo, we have assumption that attacker is already put this DLL file in Windows temp folder. And let's look how it will be in real Exchange server. First of all, it's our malicious library with our gadget. Here is our type name and 2 lines of code. We will take a CMD query parameter and we'll use its value for starting new process. As we told you earlier, this DLL file is already on Windows temp folder. So we can start crafting our request. As you can see, we are using SAML token. Here is our vulnerable attribute, type name, and assembly name is .trick that will change current folder to Windows temp. And finally, we would like to start calculator. Here is the same. First of all, let's check in Process Explorer that no calculator yet, and we can send this request without any authentication, and we can see calculator on the Process Explorer. Now let's switch to our Holy Grail and we'll look how the entire signature verification can be bypassed. Security assertion markup language, or just SAML, is a critical component for many delegated authentication and single sign-on scenarios. It has XML-based format and uses XML signature for integrity protection. By the way, this problem is relevant not only for SAML, but for other protocols and applications that uses XML signature standard. For example, SignettSoap or WS Security. On this slide, we can see simplified SAML token. Along with authentication information, it has signature element that should protect it from tampering. This element contains 3 main parts. Signature itself in signature value, signet info with information how this signature should be verified, and the most interesting element for our attack, it's key info. Represents key that should be used for signature verification. SAML protocol is quite old protocol, and of course we are not the first ones who decided to look on its security. So we would like to highlight a couple examples of interesting findings from the past. For example, XML signature wrapping discovered in 2012 and allows attacker to change original token, but signature remains valid. The second our example was presented last year by Kyle B. Ludwig, and he uses XML comments to change meaning of some token attributes, but signature remains the same. Both examples require valid token and will not change signature. Our attack is different. We are able to recalculate own signature and create SAML token with any information what we would like. So we do not need to have valid SAML token at all. For understanding how it's possible, we should know how .NET implements signature verification. So first of all, we need to obtain key. Using key info, we can extract key itself from it, or use a key reference to fetch key from some storage. On the second step, using this key, we will verify signature value. But please note, after this step, if you have a positive result, it only means that this token was signed by this key and it was not changed. In addition to this, we should be sure that it was done by proper signing party. So we are taking key info element again, try to identify who has signed this token, and of course on the last step we will check it is expected signing party trusted or not. On the first glance it may look like secure implementation, but please pay attention on these two steps. We are taking key info twice, and we need different type of results on these steps. Security key on the first and security token on the second. So we need to use different methods for it. Resolve security key and resolve security token. On this slide we can see a description from Microsoft documentation. Because purposes of these methods are different, we can expect inconsistent results from them. And finally, we can see the general idea of our attack. We should craft key info in such a way that both methods will produce different results. One will be used for signature verification and another for authentication of signing party. In this case, we will be able to use own signing as our own key for signature calculation, but server still identify us as expected signing party. In general, such attack depends on. Sorry. Do you hear me? So in general, such attack depends on implementation of the mentioned methods. But all cases with what we checked, we were able to get these results. Some cases had additional requirements to the server or environment, we will show a bit later. Others were vulnerable by default. So let's see examples of differences between this method that can be used for attack. First method can support some type of key identifier that is not supported by the second one. Both methods can process elements in different order, or even they can use different subset of these elements. Now let's see how this attack looks on real world application and frameworks.
So yeah, we will be reviewing some of the most important frameworks in Microsoft that actually take or accept SAML tokens. So the first one will be WCF. We will see that in a few seconds. That is basically used to build web services. like for example, Exchange Server, and we will show you an example of how we can take any account or compromise any account using this technique. The second one will be Windows Identity Foundation, that is basically used for any application that wants to integrate with an identity provider. So if you want to process authentication tokens and extract the claims, you don't want to do that from your own, like reinvent the wheel. You will be using Windows Identity Foundation to take care of that process. And last but not least, we will see how some applications like SharePoint actually customize the configuration of WIF and can make it even more vulnerable than in the default configuration. So the first framework is Windows Communication Foundation. As I said, it's used to build web services. It's a Microsoft framework, but it's used to build service-oriented applications, which basically interoperates with other web services and clients developed in other languages and frameworks. It will basically exchange XML documents that are in the form of SOAP messages, but the most important part for us is that it will accept SAML tokens to authenticate the client. So if you are a client, you can present your credentials either with maybe user and password, but you can also submit a SAML token in order to authenticate yourself. So depending on the version, it may use Windows Identity Foundation to take care of the process of handling the authentication token or not. We will start by focusing on when it's not using WIF, and then we will review when it's using WIF because it's different resolvers and different attack. So the class that is responsible for handling the token, the authentication token, in this case the SAML token, is this SAML assertion token, SAML assertion class here, and it will basically contain this piece of code. So as we can see, we have the two methods that Alex mentioned. The first one is the resolve security key that will take the whole key info section. So this key identifier variable is the whole key info section. And the other method is resolve security token that takes the same data, and this is user control data. But both of them return different elements, different objects. The first one will be returning the verification key, that is the one that will be used to verify the signature of the SAML token. And the second one will be returning the signing token that is used to verify that it was signed by the identity provider that the service trusts, not anyone. So the first one, when resolving the security key, this is the code. It basically takes what we call depth-first approach. So it will basically iterate through all the different keys in the key info section. There may be multiple. Normally it's only one, but the standard allows multiple of them. So many of them. So it will iterate through all of them, and for each of them, it will call this try resolve security key down here. So this method will basically try a number of different resolvers. We have at least 3 of them in order to try to extract and resolve the key. So the important thing here is that we are first iterating through the keys and then through the resolvers. Now, if we check how the token is resolved, that's what we call breadth first. And it's going a slightly different approach. It's first iterating through the resolvers. And for each resolver, it will pass the whole key info section and will basically iterate through all the keys, individual key elements. So basically, it's like having 2 nested loops. In the first one, we will be iterating first for the keys and then resolvers. And in the other one, first resolvers. And the second one, or the second level, will be iterating through the keys. So we will be basically iterating through the same elements, but in different order. And when changing the order, we can actually abuse that in order to bypass the signature process. So now let's imagine we have a token, or we can even create one token from scratch, and we will sign it with our own symmetric key. We generate a symmetric key, or even an asymmetric key, but for this example, just keep with the symmetric key. And we'll sign our own token with our own key. It should not be trusted, right? Now we're going to send both the symmetric key, but also the expected and trusted certificate from the identity provider. We're going to send 2 elements in this key info section. Now, the resolve security key will iterate first through the keys and will take our malicious symmetric key. Then it will try all the resolvers for this key. And the 2 first resolvers will fail, but the third one will succeed. and it will return our symmetric key that will be used to verify the signature. Since we control it, we can bypass it. Now, the resolve security token down here will basically do a different approach and will first iterate through the resolver. So it will take the first resolver, and with that resolver, it will try to resolve the two key elements here. So the first one will fail because it will not trust a symmetric key that it doesn't know. But for the second one, it will succeed because it's actually the certificate from the identity provider. So it will return that certificate, and that certificate will be used to authenticate the signing party that is the identity provider. So now we are able to bypass the signature and just basically craft any arbitrary tokens. So this is how it looks in the XML token. We have this first element that is, in this case, a symmetric key, but it could be an asymmetric one. And that's the injected key, the one that we will use to resign the document and the one that the server will use to verify the signature. And the second one in green is actually the original trusted certificate from the identity provider. And this one will be the one that the server will use to verify the trust in the identity provider. So let's see how we can abuse that, for example, to take over some account in Exchange web services. So we thought about doing this demo using a real client, such as Outlook or Link, but the demo was kind of complex and longer, so we developed our own client for the Exchange WS. But you can even craft your token without intercepting any real tokens. You can just craft it and sign it, and it's still valid. But for this demo, we prefer to intercept a real token and modify it. So this is Burp. Basically, we will be using Burp to intercept this client request. And this is the client that we developed. It's very simple. We are just sending a request for user one in the name of user one, and we are basically requesting the mail tips. We could have asked for the mail items themselves, but this is more simple. So we send that, and we intercept the request. And if we send that to a repeater in order to modify it like more easy, we can switch to XML view, and we will see the whole SAML assertion first in the header, in the SOAP header, and then the body of the SOAP request. So we will be replacing all the instances of user one with administrator. If we don't resign this, if we just basically intercept a request and we just modify it, we will break the signature and this will not be valid, right? So if we send the request like this, we will get an internal server error because it's not able to verify the signature. We just broke it. However, we developed this plugin for Burp that we will be releasing, and it will allow us to resign it with our own keys. So in the original assertion, you can see that there is only one element in the key info. That is the expected identity provider certificate. Now, if we click on resign with RSA key, it will basically create a new RSA key pair and then use the private one to resign the whole token. And then in the key info section, we will find the one from the identity provider, but also our own RSA key. That, remember, this one will be used for verifying the signature. So now if we send that, we'll get a 200 response, which is successful. And we can see that we are able to get, in this case, the mail tips for the administrator. And we get no errors, and the response was successful. So with that, we are able to basically impersonate any user in Exchange web services.
Doesn't that only work when you're not using secure protocol to send the data to the SAML assertions over?
You mean like transport protocol, transport security?
GTL.
Doesn't matter because you're crafting your token from from the client, and in this case, we are intercepting it. But if you don't want to intercept it, you can craft the same token yourself and just sign it. So interception is just one version of the attack. Also, if you control the client, you can use Burp to intercept the traffic for that client, even if it's using SSL. OK. So Windows Identity Foundation.
It is another example of affected tool framework. Windows Identity Foundation, or just WIF. is a software framework for building identity-aware applications. It is very easy to add a delegated authentication to your application and support authentication tokens from different security tokens services like Active Directory Federation services, Azure Active Directory, Windows Azure Access Control services, and others. For parsing SAML tokens, WIF uses SAML security token handler, and it uses a bit different approach to the key info element that we just saw in previous section. For a security key, to verify signature value, it will take only the first element of our key info. But for security token, for our authentication of signing party, it will work with all key identifiers from key info. Also, WIF by default configuration uses issuer token resolver. This resolver seems to be secure because it has very similar code for both mentioned methods. But in case if this method cannot resolve some key identifier, it will be passed to the next resolver, X509 certificate store token resolver. And here we have difference in the mentioned method that can be abused. A resolve security key can work with encrypted key identifier clause, but resolve security token doesn't support it. Definitely this difference can be exploited, but here we have a couple problems. To decrypt our symmetric key, server needs to have certificate with private key in some specific certificate storage. By default, it's local machine trusted people. Also, attacker would need to use public key from this certificate to encrypt this key. And it is just public key, so in many cases it is not a big problem. But if these requirements are met, we can perform our attack. So we can use symmetric key for signature calculation. After that, we can encrypt this key using public key from server certificate and put encrypted key identifier clause in the first place. After that, we will put our expected certificate. So resolve security key will return our symmetric key, and we will pass signature value verification. But resolve security token doesn't work with encrypted key identifier clause, so it just skip it and will take the second element from key info, and it represents expected signing party. So we will pass authentication of signing party as well. On this slide, we can see examples of key info for this attack. Encrypted symmetric key in cipher data. Internal key info in yellow section represents certificate which public key was used for encryption, and this similar to previous case, in green section it's expected certificate. We were reviewing default configuration of WIF, but it allows a lot of customization. So let's review some example of customized WIF.
So if you are using WIF to build your application, you can customize it. And one of the major products or Microsoft products that customize WIF is SharePoint server. So it's a very interesting target for us. And we analyze how SharePoint customizes WIF for their own purposes. So it basically uses a standard or default configuration, but it uses a default issuer token resolver, the SP issuer token resolver. And remember, this is using WIF, so for security keys, we only process the first element in the key info section, and for security token resolution, we use all of the elements in the key info section. Apart from that, the key resolution supports symmetric and asymmetric keys. They are called internally like intrinsic keys. but for token resolution, it doesn't support them, right? So we can abuse that in a very similar way to what we did with Exchange by resigning our token or crafting a token from scratch and then signing it, and use our own private RSA key to sign it, and then send the public key of this RSA key pair along with the original and trusted certificate to the server. Again, the server will take one for signature verification and take the other one for authentication of the signing party, and we will be able to abuse that in order to make the server use our own RSA key for verifying the signature. So this is how it looks in XML. It's very similar to what we saw in the Exchange demo. It's using an RSA key. As you can see here, we are sending the modulus and the exponent for the public key. This is what is an intrinsic key, something that can be recreated out of this data. And then, obviously, the original and trusted certificate for the signing party. So we thought, like, yay, now we can abuse and attack SharePoint, but we found another problem. So this is how the authentication flow works for SharePoint, more or less. If there is any Microsoft engineer in the room, please correct us if we are wrong. But basically what the user is doing is requesting an authentication token from the IDP, from the identity provider. It may be ADFS or Azure Active Directory or any identity provider. And with the authentication token, it will present it to SharePoint. So SharePoint will validate that using the token resolver that I just showed you, the SP issuer token resolver, which is vulnerable, and we can abuse that and make it trust our signature and then bypass the signature verification. Okay, so far so good. But now SharePoint doesn't want our SAML token. It will exchange that token with internal SharePoint STS, that is a security token service, in order to get an internal local session token. And this other service that is implemented as a WCF web service that is using WIF is using the WIF default resolver, which Alex explained that in order to attack these configurations, we need to get access to the public certificate that is stored in the SharePoint server. This is somehow a strong limitation, and we didn't want to go this way because it's not that funny. So what we did, we found a different flow. Basically, it's not a flow, but a different way that we can abuse to exploit it. So in step number 6, you can see that the session token is cached, right? And then out of this session token, it generates a session cookie that is returned to the user. Now, in order to attack SharePoint using this technique, what we can do is authenticate as a valid user, as the attacker, maybe with a low privilege account, and then get our session cookie. In this process, the session token for the attacker will be cached. And the cache key will be an internal identifier for the attacker, right? Just remember that. Now, what we will be doing is basically crafting a malicious token from scratch that will have some very specific claims. So first of all, the issuer will be SharePoint. It will not be the identity provider. And then we will use the victim data, or the victim attributes as the, for example, user principal name, user ID. So the token will be representing the victim, but we will send the attacker internal ID as the cache key. So now SharePoint will receive that. It will verify the signature. We will bypass that. And then because the issuer is SharePoint, it will not try to exchange the token with the STS, the security token service, and will basically create a session token out of this data. So we are basically creating a session token for the victim. But when storing it in the cache, we will use the attacker cache key. And therefore, we will be poisoning the cache and basically replacing the session token for the attacker with the victim one. So now all that the attacker needs to do is refresh the browser, browse again to SharePoint, and then it will get authenticated as the victim. Now, if you do that for administrator account, that's basically a remote code execution. So last demo. So here we are, as the attacker is browsing to SharePoint, and is basically going to authenticate with valid credentials. As I said, maybe low privilege, or maybe he wants to escalate privileges to get remote code execution. Now, we will just get authenticated as the attacker, as you can see here. So far, nothing special, no attacks, just basically logging in as a user in SharePoint. Now we can go to this endpoint that is an API endpoint to get information about the users in SharePoint. It's public, and you can access that if you have an account, any account. So that returns a piece of XML that, I'm sorry for the font size, but I will zoom in very quickly. So basically, if we search for the attacker, we want to get the attacker internal ID. So you can see that the attacker internal ID is this long string with some information about the email address and the identity provider and so on. And now if we search this document for the victim, we will get the victim internal ID. So this is the information we need to craft our malicious token. And then because we can resign it using our key confusion attack, then it will be accepted. So this is the code to craft this malicious token. We will be using the victim internal ID, but for the application token cache key, we'll be using the attacker one. And this is what will allow us to replace and poison the attacker session token. So this is the token that it generates. As you can see here in the key info section, we have two key identifiers. The first one is the RSA key value. That is the one that we use to resign it, the one that we control, and then the key identifier that SharePoint trusts. Now, if we scroll up a little bit for the SAML claims or attributes, we can see that we have the user ID, and everything points to the victim, right? The user ID, also the user email address, the UPN, but the application token cache key, that is a special claim, will point to the attacker internal ID. So now, if we send this request, SharePoint will basically replace the attacker session token in the cache with the victim one. And now we just have to go to the browser, refresh the session, and then we will get authenticated as the victim. And remember, if you do that for administrator, that will lead to remote code execution. So, we are releasing this Burp plugin. It's not ready yet. Will be probably released tomorrow after Black Hat talk. It will be released in this repo, that's for sure. And it will basically allow you to intercept SAML assertions, SAML tokens, and just modify them and use either an RSA key to resign it, or if you get access to the public certificate in the case of a WIF application, then you can import it down here and then resign it. So there will be instruction and more information in the repo probably tomorrow. So with that, some few conclusions. Basically, we are not saying that SAML protocol or WS Federation protocols are insecure. It's basically that some implementation has some flaws. In this case, the flaw in the .NET implementation is that they are processing the same user control data with different methods, and they are slightly differently processing this data, right? And we can abuse that in order to make one of the methods process one key and the other one process a different key. Also, we focus on researching .NET libraries and framework because basically it was not vulnerable to any other attacks before, any of the other attacks that Alex presented. And we didn't review any other languages or frameworks. We don't expect this very same flow to be present in other languages because it's somehow specific to .NET and how it handles keys and tokens in a different way. But there may be similar flaws out there in other languages, libraries. Also, even in .NET, XML signature, remember this is a vulnerability that affects SAML token verification, but the vulnerability is in the way that XML signature is processed. And basically, XML signature is used in a lot of other places. We found other cases that we reported to Microsoft, and they patched them, but there may be other cases where XML signature is still insecure. Main takeaway, patch as soon as possible if you have any SharePoints or Exchange servers on-premise, because obviously the cloud ones are already patched. And with that, if you have any questions, I think we have still some minutes, or you can reach us in Twitter. These are our Twitter handles. So thank you very much.
We have a little more than 5 minutes, and let me remind you, please raise your hand, and I'll run the mic to you to ask questions, so people watching online are able to see it, or hear it, I mean.
Oh, all right. Hello, that's just fascinating. That's really excellent work. I'm wondering whether you see the problem in the SAML specifications. Are they vague about how multiple key information is supposed to be processed? Or are the standards clear and the implementations where the problem is?
Yeah, so normally you will always find that key info section contains only one key. That's like 99% of the cases. But actually the standard allows multiple keys, but it doesn't define how they should be treated. And probably one of the use cases is because you may do key rotation, and then you may send the actual one, but send the next one to be stored by the client or something like that. But I don't think that is documented. It's a legal case, sending multiple keys. Actually, Microsoft support them, but because it's not very normal, I think that it's not handled or it's not tested very thoroughly. That's our assumption. Thank you.
Hi there. What version and build of Exchange was that demo done in?
Okay, so it was. Do you want to answer this one?
Yes, it's Exchange Server 2019, and was before last Tuesday patch, because last Tuesday patch solved this problem. I think it's something like in the spring. I cannot tell you exactly building number, but it's quite fresh. It was done in the spring. In this spring.
There's another question.
By the way, problem is not in Exchange server. We just want to highlight again. Problem in .NET framework libraries. It's we do not see any string dependency on the build of Exchange server.
What are the best practices to be able to shut down this type of attack? I mean, if you use different, if you can't get the public key for that particular machine, as far as using a different public key for the internal trusted store versus what the web server presents, what's the best way to shut it down other than patching?
To be honest, we were shocked to see that this key info is it's processes twice. Why we need to do this twice? Secure way. Just take one times. Take what you need, token, key, and other stuff, or at least verify that they are connected somehow. Here, there's no verification that they are connected. The key is from token or token from key, and we believe that proper implementation should choose this way, or check connection between the results, or use only one method, one approach for both results.
So other than that, for patching, other than patching, the other thing that you can do, you said that not make public or not expose the public certificate of those certificates stored in that particular certificate storage, but that's only for Windows Identity Foundation. For WCF, for SharePoint, that doesn't matter. So the only way of real patching the issue is by applying the latest security patches. Also for SharePoint, for example, you need to upgrade to the latest version of SharePoint, but also get the latest version of the identity model library through NuGet. So you better go to the Microsoft page for this CV, because, for example, in SharePoint, it's not straightforward. It's not just as simple as upgrade the SharePoint version to the latest version.
I'm just curious. It sounds to me like this is all on-prem. Is this a problem on the O365 platform? And
it used to be.
It used to be?
Until the July Tuesday patch.
Ah. Okay.
So the good thing is that because it's Microsoft infrastructure, they already patched that. So online version, cloud version is patched. Now it remains the on-premise leftovers. If your companies are using on-premise services, those need to be patched.
Now, along with that, though, was it defeated by in O365 by MFA or not?
Say that again, sorry?
Was that actually preventable by MFA, multi-factor authentication, or not?
That's a good question. So if SAML token requires a second factor, then yeah, it will be prevented by that, because the SAML token will be just one of the factors. Good question, thank you.
We have time for one last question if somebody wants it.
Been exploited in the wild at all? If it's been around for several months, I mean, that's especially if it's on 0365, then it's
No,
quite
that
large.
we know of. I mean, we don't have access to Microsoft monitoring systems for example, 0365.
So there's no reports of it being exploited, not even any on-prem solutions. Are there any solutions that detect this sort of attack now that it's been implemented in?
Guys, it was not publicly available, this information. We just knows about this and reported to Microsoft. Microsoft knew about this for a couple of months, and we can understand Microsoft because if you can see description for CVE, there are huge of product that should be patched, including .NET Framework and other stuff. So it was not publicly available, this information. It's first time when we presented. So we were not exploiting nothing, and hope nobody.
We promise.
Yep. So it was known for Microsoft for a couple months, but it was known just Microsoft and us.
Is there a way to find out if someone has been exploited with this at all? Would there be any sort of log or any kind of reference in any auditing on any on-prem system?
We have no idea. I mean, we can't be 100% sure that, I don't know, someone in China or in Russia knew about this vulnerability and was exploiting it. As soon as we found it, we reported it to Microsoft, and as far as I know, in the CVE report, they say that it's not exploited in the wild. So I don't think that they have evidences that it's been exploited in the wild.
Okay, all right.
So this is the CV number for the Dupe Key Confusion. You will find a lot of information in Microsoft bulletin about how to patch it, if it's exploited in the wild or not.
Thank you all for coming out. Please thank Alexander and Alvaro, and support our sponsors,